Hello students. The topic that we are going to discuss today is moving charges and magnetism, NCERT section 4.8 to 4.9.1 and example 4.9 to 4.10. So this is the disclaimer. The learning objectives. By the end of this lecture, you will be able to understand the concept of force between two parallel currents, analyze the behavior of a current carrying rectangular loop when placed in a uniform magnetic field, derive the expression for torque experienced by the loop placed in uniform magnetic field. So this is the index of topics that we are going to cover today. NCERT section 4.8, force between two parallel currents, the ampere. Example 4.9, NCERT section 4.9, torque on current loop magnetic dipole, in which we are going to discuss today 4.9.1, torque on a rectangular current loop in a uniform magnetic field, and example 4.10. So let's start our first topic, that is NCERT section 4.8, force between two parallel currents, the ampere. So we are going to derive force per unit length on current carrying conductor. So this is the diagram. There are two conductors. There are two parallel conductors, long parallel conductors. Okay. So they are carrying current in the same direction, IA and IB. There are two conductors A and B. They are carrying current IA and IB respectively. And the separation between them is D. Okay. So figure 4.17, two long straight parallel conductors carrying steady currents IA and IB and separated by a distance D. BA is the magnetic field set up by conductor A at conductor B. Okay. So due to the flow of current in conductor A, there is a magnetic field lines or magnetic field around the conductor A. So due to the magnetic field of the conductor A, the force experienced by conductor B is to be calculated. Two current carrying conductors placed near each other exert magnetic forces on each other. Okay, so that magnetic forces we are going to calculate now. So during period 1820 to 1825, Ampere studied the nature of this force, and it depends upon the force between two straight long conductors. The nature of this force and its dependence on the magnitude of current flowing through conductors. Okay, this force between the two parallel long conductors is depends upon the magnitude of current flowing through the conductors, the shape and size of the conductors, and third one is the distance between the conductors. So the force between two parallel long conductors depends upon these three factors. So figure 4.17 shows two long parallel conductors A and B placed horizontally that are separated by a distance D. You can see in the diagram also, carrying parallel currents IA and IB. A conductor is carrying current IA and B conductor is carrying current IB. Conductor A produces magnetic field BA along conductor B in downward direction. Okay, so due to the flow of current, we can take the magnetic field of B also. Okay, so now we are going to take magnetic field of one conductor, any conductor. So we are going to take the magnetic field of A conductor. So conductor A produces magnetic field BA, okay, along the conductor BA in the downward direction. So you can see, using right hand thumb rule, you can find the magnetic field lines or direction of magnetic field around conductor A. It is in the form of concentric circles, and direction is direction on B. Direction of B conductor, you can see after curling your fingers, when your fingers reach the B conductor, the direction, the fingers point in the downward direction. So magnetic field is in the downward direction. Magnetic field produced by conductor A is in the downward direction along B conductor. The right hand thumb rule tells us the direction of the magnetic field BA along B conductor. Got it? Magnitude of BA is given by Ampere circuital law. Okay, so magnetic field produced by a long straight conductor. We have discussed in our previous lectures. It is the expression is being given by Ampere circuital law, which is equation 4.15a. So magnetic field produced by a straight long conductor carrying current is given by B equal to mu naught I upon 2 pi d, या 2 pi r. Okay, so we are going to find the what is r, the distance of point from the center of the wire where we are going to find the magnetic field. We are going to find the magnetic field at B conductor here, and magnetic field is being produced by A conductor. Okay, so BA magnetic field due to A conductor is equal to mu naught IA current flowing through A conductor upon 2 pi d. So the distance where we are going to find the magnetic field is the distance between the two conductors. We are going to find the magnetic field at B conductor. So BA is equal to mu naught IA upon 2 pi d, where d is the distance between two conductors and IA is the current flowing through conductor A. Now conductor B carrying current IB experiences a sideways force due to BA. Okay, so this conductor B, due to the magnetic field produced by A conductor, this conductor B, which is carrying IB current, will experience a force, a sideways force. Okay, due to BA. What is this force? The direction of this sideways force is towards A. Now, what is this force? You have also learned about the Lorentz force. Force on a current carrying conductor placed in a external magnetic field. Okay, we have discussed in our introduction or first topic where Lorentz force is being introduced. Okay, in that Lorentz force there was a topic named force experienced by a straight conductor or force experienced by a conductor carrying current in the magnetic field. Okay, then there we have discussed what is the force. Force was F equal to I L cross B, ILB sin theta. That force we have discussed in our first topic, Lorentz force. Okay, so this is that type of force. Magnetic field is being produced by A conductor, and this magnetic field is being experienced by B conductor. So B is experiencing force due to the magnetic field produced by first conductor. Okay, so that force is basically force experienced by the current carrying conductor in the external magnetic field. Okay, so external magnetic field is due to conductor A. So direction of this sideway force is towards A. Now how we can find the direction of this? By right hand rule for vector product. You have to align your fingers in the direction of L or in the direction of current. Okay, align your fingers in the direction of IB current. Now curl the fingers in the direction of B, magnetic field BA. Curl the fingers, align your fingers firstly in the direction of IB, and now curl the fingers in the direction of BA, magnetic field. Now your thumb will give the direction of force acting on this conductor. Now you can see force is towards the A conductor. So direction of force can be found using right hand rule for vector products. Okay, now you can see FBA, force on B conductor due to A conductor, FBA. It is towards A conductor. The magnitude of force FBA on segment L of segment L of B due to A is given by equation 4.4. Okay, now we have to discuss about the segment L only. We are going to find the force per unit length. Okay, force, they are very long conductors. We cannot consider the length. If the conductors are infinite or very long, we cannot measure the length. So we are going to define the force per unit length. Okay, this capital FBA is the total force experienced by the whole conductor B. Okay, so now magnitude of force FBA on segment, only L segment we are considering, of length L. In the diagram it is shown this segment of conductor B of length L. So magnitude of force FBA on segment L of B due to A is given by equation 4.4. So what is the force experienced by a conductor of length L is given by F equal to ILB or BIL. IL cross B, that we have derived, IL cross B, ILB sin theta. So what is the theta here? Angle between L and B. So L or current, direction of L vector is same as current. So IB is in horizontal direction and magnetic field is in downward direction. So angle between IL or B is 90 degree. So sine 90 degree is 1. So ILB. So force is ILB. So FBA is IB, current flowing through that conductor IB, L, and magnetic field, that is BA. Got it? So after putting the value of BA, so we have also calculated the value of BA, put it here. FBA is equal to mu naught IA IB. What was the value of BA? Mu naught IA upon 2 pi D. Put this value in this expression, you will get FBA equal to mu naught IA IB upon 2 pi D into capital L. L is the length of that segment we are considering here. Mark it as 4.17 equation. Now, similarly, force FAB. Now, we have calculated the FBA. Now, what is FAB? Is the force experienced by A conductor due to the magnetic field produced by B conductor. Now, we are reversing the situation. Now, we are calculating the force experienced by A conductor due to B conductor. Now, steps are same and you will see also that result will also be same. But direction of force will be different. Magnitude will be same. Okay. So similarly, force FAB on segment L of A due to B is equal in magnitude to FBA. FAB will be equal to magnitude FBA, but direct towards B. Now FBA is directed towards, its direction is towards A conductor. Now FBA is directed towards A conductor. So FAB is directed towards B conductor. You can see also magnetic field produced by B conductor by right hand thumb rule on along A, it is in the upward direction when you find it using right hand thumb rule. Okay, so curl your fingers, align your thumb in IB direction. Along A conductor, magnetic field is perpendicular to the plane and outwards, or we can say upwards. Okay, now in the magnetic field is in the upward direction, current flowing through A conductor is in IA is shown also. So align your fingers along IA and curl them towards the B, which is in upward direction in second case. So force will be in direction of towards B conductor. Okay, so magnitude of FAB will be equal to FBA, but it is directed towards B, which is, that means it is in the direction opposite to FBA, exactly opposite. So we can say FBA is equal to minus FAB. Magnitude is same, but direction is opposite. So FBA is equal to minus FAB. Mark it as 4.18. This follows Newton's third law. Okay, this is in accordance with Newton's third law. So Biot-Savart's law and Lorentz force, both are using here. We are using here. So we are using Ampere's law here, or we can find the magnetic field around straight conductor using Biot-Savart law also. Okay, and Lorentz force is also being considered here. Okay, so Biot-Savart law and the Lorentz force yield result in accordance with the Newton's third law. Parallel currents. Now you can see here direction of current in both the conductor is in same direction. Okay, so direction of current is same in both the conductors, so they are parallel currents. So now we can see that direction of force is direction of force on one conductor is towards another conductor. So you can see they are attracting each other. In this case that we are discussing, conductors are attracting each other. Okay, this force on this B conductor is towards A, and force on this A conductor will be towards B. So they are attracting each other. So parallel currents attract each other. But if we are considering the current in the opposite direction in both the conductors, then they will repel. You can see, or you can find the direction by using right hand thumb rule also. So while anti-parallel currents repel, this is very important conclusion, that parallel currents attract and anti-parallel currents repel, opposite to electrostatic behavior. What is electrostatic behavior? That like charges repel and unlike charges attract. Okay, but it is opposite to electrostatic behavior. Parallel currents attract and anti-parallel currents repel. Now let small FBA represent the force FBA per unit length. We have to find the force per unit length. If the length of the conductor is very long or infinite conductors are there, so we have to find the force per unit length. So small FBA represents the FBA per unit length. So we are dividing FBA by L. So from equation 4.17, FBA is equal to mu naught IA IB upon 2 pi d. This is the force per unit length on B conductor due to A conductor. The above expression is used to define the ampere. So this expression is if we are going to find the magnitude of force, okay, either on A conductor or B conductor, magnitude will be same. So FBA is equal to FAB, which is equal to mu naught IA IB upon 2 pi d. Okay, but only direction is different. The above expression is used to define the ampere. So we are going to define the ampere by using this expression. So ampere is the value of that steady current which when maintained in two long straight parallel conductors. Okay, so 1 ampere is that value of steady current, not variable current. When maintained, when this current is flowing through two very long straight and parallel conductors of negligible cross section area. What is the significance of writing negligible cross section area? Which means the conductors are nearly infinite, very long conductors, because their cross section is negligible as compared to length, and placed 1 meter apart, which means D will be equal to 1 meter in vacuum, then would produce force equal to 2 into 10 to the power minus 7 newtons per meter of length on each conductor. Okay, so what is 1 ampere? Now we can read it collectively. 1 ampere is the value of steady current which when maintained in two very long straight parallel conductors of negligible cross section area and placed 1 meter apart in vacuum would produce force equal to 2 into 10 to the power minus 7 newtons per meter of length on each conductor. This is the definition of 1 ampere here. This theoretical definition of ampere was adopted in 1946. But in practice, one must eliminate the effect of Earth's magnetic field. Okay, so for practice or actual practical applications, one must eliminate the effect of Earth's magnetic field and substitute very long wire by multi-turn coils of appropriate geometries. The coulomb can now be defined in the terms of ampere. So the SI unit of charge can be defined in the terms of ampere now. When a steady current of 1 ampere flows through the conductor, charge flowing through cross section in 1 second equals 1 coulomb. This is the same definition. Now example 4.9, the horizontal component of Earth's magnetic field at a certain place is 3 into 10 to the power minus 5 Tesla, and the direction of field is from geographical south to the geographical north. Okay, so from south to north is the direction of magnetic field of Earth, and magnitude is 3 into 10 to the power minus 5 Tesla. Okay, so direction is from south to north. A very long straight conductor is carrying a current of 1 ampere. What is the force per unit length on it when it is placed on a horizontal table and the direction of current is, first case, east to west. When direction of current is from east to west and magnitude of current is 1 ampere, we have to find the force per unit length. Okay, so let's see the solution. Force on a current carrying conductor placed in uniform magnetic field is given by F equal to I L cross B. This is the Lorentz force we have discussed already. So F is equal to I L cross B. So ILB sine theta. When magnetic field is from south to north and current is from east to west, the direction between angle between L and B is 90 degree here. Got it? Magnetic field is from south to north. Current is from east to west. Okay, so direction of L vector, length vector is same as current. Okay, so direction between angle between L vector and B is 90 degree. The force per unit length is given by small f is equal to F upon L, which is IB sine theta. Okay, so now A, when the current is flowing from east to west, theta is 90 degree. Hence, we are going to put it in the expression of force per unit length, which is IB sine theta, IB sine 90 degree equal to IB. So F equal to what is I, 1 ampere, what is B, 3 into 10 to the power minus 5 Tesla. So force per unit length of the conductor is 3 into 10 to the power minus 5 Newton per meter. So now this is the larger than the value of 2 into 10 to the power minus 7 Newton per meter quoted in the definition of ampere. So in the definition of ampere, this is the force per unit length between two conductors, that is 2 into 10 to the power minus 7 Newton per meter. So the value we have calculated for now for conductor given in the question is greater than this value, 2 into 10 to the power minus 7 Newton per meter. Okay. Therefore, it is important to eliminate the effect of Earth's magnetic field while standardizing the ampere. Okay. So due to Earth's magnetic field, we have calculated the force on the current carrying conductor, which is greater than this value, 2 into 10 to the power minus 7 Newton per meter, which is quoted in the ampere's definition. So to define the ampere, to standardize the ampere, we have to eliminate the effect of Earth's magnetic field. The direction of the force is downwards. Okay, you can find the direction of force also. Align your fingers in the direction of current, which is east to west. Okay, now curl your fingers in the direction of magnetic field, that is from south to north. Okay, so what is the direction of force? Wire is placed horizontally. Okay, so what is the direction of force is downwards. Direction may be obtained by right hand rule for cross product. Okay, align your finger in the direction of current. Wire is placed horizontally. Curl your fingers in the direction of magnetic field and thumb will give the direction of force. Now B part. When direction of current is from south to north. So when the current is flowing from south to north, magnetic field is also from south to north. So theta will be equal to 0 degree. Hence, F equal to IB sine 0 degree. So which is 0. So hence there is no force on the conductor when the current in the conductor is from south to north. Okay, now quick revision of torque, because we are going to discuss the topic torque on a rectangular loop. So we have to learn about torque first. So there is a quick revision of torque here. So definition of torque torque tau is analogous to force in rotational motion. Okay, in linear motion we discuss about force. So torque is analogous to force in the rotational motion. Like angular velocity is analogous to velocity. Angular acceleration is analogous to linear acceleration. Similarly, torque is analogous to force in rotational motion that causes angular acceleration. Force causes linear acceleration. Torque causes angular acceleration. It is the cross product of position vector and force. Okay, so vector form of torque is given by R cross F. What is R? Position vector from the point where we are about which we are going to find the torque, and to which point where force is being applied. From point where about which torque is we are going to find the torque, and to the point where force is being applied. So this is the position vector from point to point. Okay, and F is force. So direction of torque can be obtained by using right hand rule for vector products. Okay, so right hand rule for vector products also applied here to find the direction of torque. Align your fingers in the direction of position vector and curl your fingers in the direction of force. Thumb will give the direction of torque. Magnitude of torque is given by tau is equal to Rf sin theta, where tau is torque, R is position vector from the axis of rotation, and about which from the point about which we are going to find the torque. F is equal to applied force, theta is equal to angle between R and F. Units of torque is Newton meters in SI system of units. So this is a quick revision of torque because we are going to use this terminology in the upcoming topic. Okay, now 4.9.1. 4.9 topic, that is torque on current loop magnetic dipole. Okay, in that 4.9 section we are going to discuss 4.9.1, which is torque on a rectangular current loop in uniform magnetic field. Loop can be placed in two ways. Okay, magnetic rectangular loop can be placed in two ways. Case 1, we are going to discuss this thing in two cases. First case is plane of loop is parallel to the magnetic field. First case, we are going to discuss this problem, this concept in two cases, in two orientations. First orientation or case is case 1. Plane of loop is parallel to the magnetic field. Second case is plane of loop makes an angle theta with magnetic field. Okay, so there are two cases. So let's begin with case 1. Plane of loop is parallel to magnetic field. Okay, so this is the diagram. You can see in the screen. So this loop is placed such that the plane of the loop is parallel to magnetic field. What is the direction of magnetic field? There are two poles being shown, north and south, from north to south in the form of straight line. So loop is in the plane of magnetic field. Okay. So figure 4.18, a rectangular current carrying loop in uniform magnetic field, and magnetic field is also uniform. The magnetic moment M points downwards. What is magnetic moment? We are also going to discuss later. The torque tau is along axis and tends to rotate the clock anticlockwise. The cup, and in the B diagram, the couple acting on the coil. Okay. So what is couple? A pair of two equal and opposite forces having different lines of action. Okay, so what is line of action? I'm going to explain it further. So first case is plane of loop parallel to the magnetic field. Let's start. So let us consider a rectangular current loop placed in uniform magnetic field in its plane. Okay, as shown in the figure 4.18a. Okay, for now you have to see A figure. So in A figure, magnetic loop, rectangular loop is placed in uniform magnetic field in its plane. No forces on arms AD and BC. Why? In AD arm or in BC arm, both arms, you can see direction of current and direction of magnetic field. The angle between current and means L cross B. The angle between the direction of L vector and B vector is 0 degree. Or in the arm AD, it is 180 degree. Okay. So force on a conductor, you can consider AD part of this loop, BC, part of this loop BC as a straight conductor. Okay. So this is BC is a straight conductor and current flowing through north to south. Okay. Direction of current through this section is from north to south. Magnetic field is also from north to south. Okay. So the L vector. So I am basically formalize I L cross B. But I am saying here direction of current. Okay. So I want to clear one thing for now. If I'm using current direction and magnetic field direction, it means L vector and magnetic field direction, because L vector is having same direction as current. Got it? So I force on the conductor, current carrying conductor is I L cross B, which is ILB sine theta. Okay. So angle between this BC, this L vector or current in this section and magnetic field is 0 degree. In the BC section, the angle between the current and magnetic field is 0 degree. In AD section, angle between the current and magnetic field is 180 degree. Magnetic field is from north to south. Got it? So in both cases, sine 0 degree is 0, sine 180 degree is 0. So forces on these sections of this loop, BC section and AD arm, AD arm or BD arm, BC arm. So both these arms are experiencing no force. So no force on arms AD and BC. Force F1 now on arm AB and on arm CD. Okay. AB arm current is flowing from A to B. Magnetic field is from north to south. So angle between current and magnetic field is 90 degree. Also in CD arm, direction between angle between current and magnetic field is 90 degree. Okay. So F equal to L ILB sine 90. Sine 90 is 1. So ILB. So length of this arm is, it is also shown B, small b. Length of this rectangular loop, arm of this rectangular loop is given B, and length of this BC and AD arm are given A. Okay. So F1 force. What is F1 force on AB arm? Okay. On AB arm, force will be ILB. What is L here? B. Small b. Okay. So F1 is equal to I small b capital B on arm AB. And direction can be found using right hand rule for vector products. Align your fingers in the direction of current and curl them in the direction of magnetic field. You can see thumb pointing in the direction downwards. So force on AB arm is in downward direction. It is also shown in the B part of the figure 4.18. Force F1 is in downward direction. Okay. Now force F2. F2 force is magnitude is also same, but direction is different. What is the direction? You can apply right hand rule for vector products. Align your finger in the direction of current, curl them in towards magnetic field direction, and your thumb will give the direction of force on CD arm, and it will be in the upward direction. Okay, so out of the plane. Net force is 0. Okay, net force is again 0. Why? Magnitude of both the forces is same, and they are acting opposite to each other. So net force on the loop is 0, but their line of action is different. What is line of action? Line of action means along which line force is acting. Okay. So this is the line of action of F1. This is the line of action of F2. So their line of action is different. There is some perpendicular distance between the line of action of both forces. That is A. That is this A. The breadth of this rectangular loop. There is perpendicular distance between the line of action of both the forces. Line of action of both the forces is not same. Means their line of action is not same. So there may be torque. Net force is 0, but net torque is not 0. These both forces will produce torque. So torque acting on the current loop is tau is equal to F1 A by 2. Now you can see the diagram B part of 4.18. Okay. So we are torque, this loop is rotating around this axis, which is passing through center of this loop, halfway of this loop, this axis. Okay. So we have to find the torque about this axis. So distance of this F1 from this axis is A by 2. And distance of this F2 from this axis, perpendicular distance, I must say, perpendicular distance of F2 from this axis of rotation of coil is A by 2 also. So what is torque? Rf sine theta. Theta here is between R and F. Between position vector and F is 90 degree. You can see in the diagram B. Between the position vector, that is from that midpoint to that line of action of force F1 or line of action of force F2 is perpendicular to the force direction. Okay, so theta here is 90 degree. So torque is equal to Rf. Okay, F for F1 is F1 and R1 is A by 2 plus F2 R2 is A by 2. So net torque is equal to F1 A by 2 plus F2 A by 2. Since F1 and F2 is same, which is equal to I small b capital B. So put the value of F1 and F2. So tau is equal to F. We are taking common F. A by 2 plus A by 2 because F1 and F2 are having same magnitude. Okay. So we are putting F1 and F2 as F. So it will become FA. Now put the value of F, which is I small b capital B into A. So the final result for torque is IAB B. Now A small a is the breadth of the rectangular loop. Small b is the length of the rectangular loop. So AB is the area of the rectangular loop. So replace small a, small b with area. So tau is equal to I capital A capital B. Capital B is magnetic field, capital A is area of the loop, which is given by capital A is equal to a small b, which is area of rectangle. Does a rectangular loop carrying steady current I in uniform magnetic field B experiences torque but no force? These are conclusions. Okay. So magnetic rectangular loop which is carrying current I in a uniform magnetic field experiences torque but no net force. Similar to an electric dipole in an uniform electric field. Okay. This is similar to electric dipole placed in uniform electric field. Okay. So electric field, electric dipole, we have discussed this concept that when electric dipole is placed in uniform electric field, it experiences torque but no net force. Okay. Now case 2, plane of loop makes an angle theta with magnetic field. Now loop is not placed parallel to the magnetic field, but loop is making some angle theta with magnetic field. Got it? Now, what is this theta angle? This theta angle is not between the plane of loop and magnetic field. It is between the area vector of loop and magnetic. Okay. As you have also discussed in electric flux, we mark the angle theta between the area vector and electric field, not between the plane of loop and plane of surface and electric field. Okay, we mark theta between, we assumed, or we represent theta as the angle between the area vector and electric field, not between the plane of surface and magnetic field. Okay, so what is the area vector? Area vector is the perpendicular vector to the surface of this loop. So this angle is between the area vector and magnetic field. Got it? So this is the confusion many students have. They consider angle theta between the plane of the loop and magnetic field, which is wrong. Theta is the angle between this area vector, which is perpendicular to this loop, and magnetic field. Okay, I hope you understood. Figure 4.19a. Arbitrary angle theta with the magnetic field B. What is B diagram? Top view of the loop. The forces F1 and F2 are acting on the arms AB and CD are indicated. Okay, so this is the top view when we are viewing from another side. Okay, so F1 and F2 are acting on these arms AB and CD. For loop at angle theta with field. Okay, so this angle theta is between, again I am saying, between magnetic field and area vector. Forces on BC and DA cancel along axis. Now, in case 1, forces on BC and AD are 0. But here forces on BC and AD are not 0, but some not 0 values. But they are along same axis, so they will cancel. You can find along this BC, align your fingers in the direction of current and curl them towards magnetic field. Magnetic field is horizontal and current is somewhat at some angle to the magnetic field. So curl your fingers, force will be in this direction, along this AB, in this direction. And on AD, force will be in this direction, along CD. Okay, in this direction. So both the forces on BC and AD will having same axis, means same line of action. So they will cancel out each other. Okay. So forces on BC and DA cancel along axis. For loop plane at angle theta with field, force F1 equal to F2 equal to IVB. Now, force acting on this AB, you can find it using right hand rule for vector products. Align your fingers in the direction of current and rotate or curl fingers in the direction of magnetic field. You will find the direction of force, which is downward direction. And also similarly, you can find the direction of force on CD. You will find that force is directed upwards, as shown in the B part of the 4.19 diagram. This part. Okay. Now, what is torque? It is RF sin theta. Okay. So the angle between R and F. Okay. Now, you can see we are going to consider. So what is the perpendicular distance? R is the perpendicular distance. What is the perpendicular distance between this line of action of F1 force and midpoint? Is A by 2. Sorry, A by 2 sin theta. What is the perpendicular distance? A by 2 sin theta. Or we can say what is the actual distance between this line of point of action of force and the midpoint. Okay, this coil is rotating about an axis which is passing through its midpoint. Okay, So from the axis, distance of point of action where force is acting is a by 2, and perpendicular distance between this line of action of force and this axis is a by 2 sine theta. Okay, so force is IVB. Force is again same, IVB sine theta. Theta is 90 degree here. On AB and CD create couple. So torque tau is equal to, in first case, it was F1 A by 2 only, because force was perpendicular to the R. Here force is not perpendicular to the R. So R F sine theta. R here is A by 2. F here is F1. But angle between them is theta. Angle between A by 2 and this F is theta. Okay. So sine theta is also there. Plus F2 A by 2 sine theta. Okay. Angle between both these is not this angle. It is this angle. This angle. If we extend this A2 in this direction, this angle. You can find it by using geometry. So after solving this, F1 and F2 both are IBB. So IAB capital B sine theta. So torque is, what is AB? Is the area of this rectangular loop. So torque is equal to I capital A capital B sine theta. Mark it as 4.21. Where A equal to AB is the area of rectangle. Now magnetic moment of the current loop. So what is magnetic moment? It is defined as product of current and area of the loop. Okay, current flowing through the loop and multiply by area of the loop. That is called magnetic moment. Its direction can also be found using right hand thumb rule. So defined as M equal to IA. Mark it as 4.22 equation and direction given by right hand thumb rule. Curl your finger in the direction of current flowing through the loop and thumb will give the direction of magnetic moment. Expression of torque becomes, now what was torque? I capital A capital B sine theta. What was capital A? Area. What is capital I? Current. So IA is magnetic moment. So it will become M capital B sine theta. So MB sine theta is M cross B. So expression for torque becomes M cross B 4.23. And this is analogous or similar to electric dipole torque. In electric dipole, we also discussed or also calculated the torque, which was electric dipole moment into electric field. Sorry, cross electric field. Electric dipole moment cross electric field. Now similarly in magnetic field, torque is calculated magnetic moment cross magnetic field. Dimensions of this torque is AL square. Dimensions of magnetic moment, which is I into A, which is ampere L square and ampere meter square. Ampere meter square is the unit of magnetic moment. For n closely wound turns, if there are n turns of this loop, we are considering one turn of this loop. If there are n turns of this loop, then magnetic moment will become M equal to NIA. For one turn, it is IA. I is the current, A is the area of the loop. So for n turns, it will become M equal to NIA. Mark it as 4.24 equation. Torque expression remains, torque will remain as it is, M cross B. Only M will change. N will appear here. If n number of turns are there, then NIA is the magnetic dipole moment. So torque will remain same, equal to M cross B. So equilibrium condition and states of equilibrium for the loop. A current loop in a uniform magnetic field experiences equilibrium when total torque acting on it becomes zero. Okay, there are two conditions, equilibrium conditions in the magnetic field when the rectangular loop will experience no torque. Okay, the total torque acting on it becomes zero. So what are these conditions? So these conditions are when torque becomes 0. It means number of turns cannot be 0. Current will be there also. And area of loop cannot be 0. Magnetic field will also be there. So sin theta equal to 0. So when sin theta is equal to 0, when theta is equal to 0 degree or theta is equal to 180 degree, that means stable equilibrium. Equilibrium states are, first state is stable equilibrium when theta is equal to 0 degree, which means area vector is parallel to the field. When area vector of this loop, which is perpendicular to the area of the loop, is parallel to the magnetic field, then there is a stable equilibrium. That means torque acting on the loop is 0. And when there is a unstable equilibrium, when theta is equal to 180 degree, area vector of the is anti-parallel to the field. Okay, when area vector becomes anti-parallel to the field, then theta is 180 degree. That is unstable equilibrium. What is difference between stable and unstable? Stable means if you rotate loop or rectangular loop by a small angle, it will come to that orientation of zero torque again. Okay, but in unstable equilibrium, if you are going to rotate it, the rectangular loop by small angle, it will not return to the unstable equilibrium condition. It will tends to align to the stable equilibrium condition. Okay, that is unstable equilibrium. So example 4.10, a 100 turn closely wound circular coil of radius 10 centimeter carries a current of 3.2 ampere. A part, what is the field at the center of the coil? You have to calculate. N is given 100 turns, radius is given 10 centimeter, and current I is also given 3.2 ampere. What is the magnetic moment of this coil? The coil is placed in a vertical plane and is free to rotate about a horizontal axis which coincides with its diameter. A uniform magnetic field of 2 Tesla in the horizontal direction exists such that initially the axis of the coil is in the direction of field. The coil rotates through the angle of 90 degree under the influence of the magnetic field. So till B part, only first statement of the question is required. N required, R required, and current required. So we can solve the first two part with this information only. What is the field at the center of the coil? What is the magnetic moment? But for further parts, additional information is given. What is this initial additional information? Coil is placed in vertical plane. Okay, and is free to rotate about a horizontal axis which coincides with the diameter. Next, a uniform magnetic field 2 Tesla is there in the region in the horizontal direction exists such that initially the axis of the coil is in the direction of field and the coil rotates through an angle of 90 degree under the influence of magnetic field. Now what is the C part? What are the magnitudes of the torque on the coil in the initial and final position? What was the initial position? When loop is horizontal to the magnetic field. And what is the final position? When loop is perpendicular to the direction of magnetic field. Okay, so D part is what is the angular speed acquired by the coil when it is rotated by 90 degree. The moment of inertia of the coil is given 0.1 kg meter square. So let's see. So first part of the question, what is the field at the center of the coil? Okay, so let's see the solution. From equation 4.12, magnetic field at the center of the current loop is given by B equal to mu naught Ni upon 2R. If there is one turn, then mu naught I upon 2R. Now there are n turns, 100 turns. So mu naught Ni upon 2R. So here n is equal to 100, I is equal to 3.2 ampere and R is equal to 0.1 meter. Hence, B is equal to 4 pi into 10 to the power minus 7, which is the value of mu naught. What is the value of N is 100. And what is the value of current? 3.2 upon 2 into 10 to the power minus 1. So pi into 3.2 is 10. So B is equal to 4 into 10 to the power minus 5 into 10. upon 2 into 10 is power minus 1. Okay, so we have multiplied it with turns also. So you can see 10 is power minus 7 become 10 is power minus 5. So we have multiplied with number of turns 100. And this 10 appeared in the second step from multiplying pi into 3.2. So it is 10 point something. So we are considering it as 10. So after solving, V will be equal to 2 into 10 is power minus 3 Tesla. The direction of field is given by right hand thumb rule. Now B part, what is the magnetic moment of this coil? So magnetic moment is given by equation 4.24, that is NIA. Okay, so radius is given. So Ni pi r square, because there is circular loop. So M is equal to 100 into 3.2 into what is pi 3.14. What is radius here? 0.1 meter. Okay, so that is 10 to the power minus 1 meter. So 10 to the power minus raised to power 2, 10 to the power minus 2. So M is 10 ampere meter square. The direction is once again given by right hand thumb rule. Direction you can find using right hand thumb rule. So let's do the C part. What are the magnitudes of the torque on the coil in the initial and final position? So given B is equal to 2T. Magnitude of torque is given by tau is equal to mod M cross B using equation 4.23, that is MB sin theta. So theta for the initial condition is 0. Thus initial torque is 0. Finally, theta is equal to pi by 2, or we can say 90 degree. And final torque is MB sin 90 degree, that is MB, equal to 10 into 2. So torque final will be equal to 20 Newton meter. Let's see the D part. What is the angular speed acquired by the coil when it has rotated with by 90 degree? The moment of inertia of the coil is 0.1 kg meter square. So from Newton's second law for rotational motion, Newton's second law for rotational motion, dl by dt, what is L? Angular momentum. dl by dt is equal to torque. What is the torque expression? In the rotational motion, torque is equal to dl by dt. L is the angular momentum, and the angular momentum is equal to I omega. So I dl by dt, moment of inertia is constant, so it will come out. So d omega by dt equal to what is the torque? Mb sin theta. Okay, so I is the moment of inertia of the coil. From chain rule, we can write it d omega by dt equal to d omega by d theta into d theta by dt. D theta and d theta will get cancel out. It will result in d omega by dt also. Okay, so it becomes equal to d omega by d theta into omega. So put this value in the above equation. Using this, we will get I omega d omega equal to mb sin theta d theta. So integrating it from theta equal to 0 to theta equal to pi by 2. So I 0 to omega final. Omega d omega equal to mb theta from 0 to pi by 2 sin theta d theta. So after solving, I omega final square by 2 equal to minus mb cos theta, limit from 0 to pi by 2, which is equal to mb. So omega final will be 2 mb upon I raised to power half equal to 2 into 10 is power 2 into 20 upon 10 is power minus 1 raised to power half. So omega final will be 20 second inverse. So let's have a quick recap what we have learned today. Force per unit area of on current carrying conductor due to magnetic field produced by another similar conductor is FBA is equal to mu naught IA IB upon 2 pi d. Parallel current attract and anti-parallel currents repel. A planar loop carrying a current I having n closely wound turns and an area A possesses a magnetic moment M. Magnetic moment M is equal to NIA and the direction of M is given by right hand thumb rule. When this loop is placed in a uniform magnetic field B, the force on it is F equal to 0 and the torque on it is tau is equal to M cross B. So there are some practice questions. First question: what factors affect the force between the two parallel current carrying conductors? Okay, we have discussed. Explain why parallel conductors carrying current in same direction attract each other. How is the ampere defined using the force between parallel current carrying conductors? And fourth question: two parallel conductors 1 meter long are placed 5 centimeter apart. What current should flow through each conductor to produce a repulsive force of 0.2 Newton between them? So thank you. Let's do DPP. So wait a minute. Okay. Two long parallel conductors carrying current IA and IB in the same direction are separated by distance d. The force per unit length is, I am marking randomly. So you can mark it by solving. Okay. So there is a time shortage. So I am marking randomly. If two parallel current carrying conductors have current in the opposite direction, they will. The ampere is defined based on the force per unit length between two parallel conductors. What force per meter corresponds to 1 ampere? A conductor carries current from east to west. The horizontal component of magnetic field is directed from south to north. The force per unit length of the conductor will be. A steady current of 1 ampere in the conductor corresponds to how much charge flowing through its cross section per second? Okay, so all the question answers are correct. Okay, so you must also do DPP daily based on your topics. Okay, thank you. I hope you enjoyed the session.